Let's talk about energy for a second. Now, energy cannot be directly measured. So if we think about if we had, let's say, a gallon of diesel fuel and we wanted to measure the energy in that gallon of diesel fuel directly, that's impossible to do because in order to do that, we'd have to go down to the molecular level and look at all the interactions between the protons, the neutrons, and electrons to determine the amount of energy in that gallon of fuel. So what we saw in section point 1 is that based on the first law of thermodynamics is that we can measure changes in energy. And delta E, or the change in energy, is defined as heat Q plus work. But when you're measuring changes in energy using this formula, the experiments have to be performed at constant volume. Now, doing experiments at constant volume is possible. It's not simple, but it is doable. But I'm going to prove to you that in order to measure delta E, the change in energy, using this formula, heat plus work, the experiment has to be done at constant volume. Now, we saw in section 6.1 that work is equal to minus pressure times the change in volume. So if I substitute this equation for work into my delta E equation, let's see what we get. We get delta E is going to be equal to Q minus P delta V. But if I'm doing the reaction at constant volume, then my delta V is going to be equal to 0. And when that term cancels, I get that my delta E is equal to QV. And the V means constant volume. So to reiterate, when I'm doing a reaction at constant volume, my change in energy is simply going to be equal to the heat. But what about reactions that are performed at constant pressure? For reactions that are performed at constant pressure, which is most reactions that you would do in a lab, a thermodynamic quantity that we call enthalpy, H, eliminates the need to measure pressure volume work. The enthalpy of a system is defined as the internal energy plus the product of the pressure and volume. So if I want to measure the change in enthalpy at constant pressure, my delta H is going to be equal to delta E plus P delta V. I don't put a delta in front of the P because I'm at constant pressure. There's no change in the pressure. Now you might remember this formula from before, that delta E is equal to heat plus work. So if I substitute heat plus work into this part of my change in enthalpy equation, what I end up with is that delta H is equal to heat plus work plus pressure times volume. Now you'll also remember from the previous slide, this formula, that work is equal to minus the pressure times the change in volume. And when I plug that into the formula, I get that delta H is equal to Q minus P delta V plus P delta V. So you can see that your two P delta V terms cancel out and you get that change in enthalpy is equal to the heat at constant pressure. That's what this subscript P stands for, constant pressure. For most changes that occur at constant pressure, delta H is more relevant than delta E and easier to obtain. In order to find delta H, we measure the heat at constant pressure only, and we don't have to consider the pressure volume work. To recap, enthalpy is used to quantify the heat flow into or out of a system in a process that occurs at constant pressure. And you'll see that we'll do a lot more calculations that involve delta H than delta E, because usually when we're doing experiments in the lab, we do them at constant pressure in a vessel that's going to be open to the environment. Of course, we insulate that vessel to minimize the heat exchange with the surroundings. But again, we're going to perform most reactions at constant pressure. So that's why we're going to spend so much time measuring changes in enthalpy. Now, since enthalpy is defined as energy plus the product of pressure times volume, which are all state functions, enthalpy itself is a state function. So we can calculate delta H according to this formula here. That delta H is going to be equal to the enthalpy of the products minus the enthalpy of the reactants. Thus, delta H is equal to the heat that's exchanged during a reaction at constant pressure. Now, if we take a look at these two scenarios down here, one of them is a physical change and one of them is a reaction. You can see that on this axis here, we don't have energy, we have enthalpy. Now, what's going on in A is a physical process. We're taking solid water, so this is known as ice. We're taking ice, we're converting it into water, which has a higher enthalpy. How is it doing that? It's absorbing heat from the surroundings. How much heat is it absorbing? Well, for every mole of ice that you're converting into 1 mole of liquid water, it's taking 6.01 kilojoules to do that. So according to the formula, delta H is equal to the enthalpy of the products minus the reactants. Since the product has a higher enthalpy and we're subtracting reactants from products, my delta H is going to be greater than 0, and we call this an endothermic process. In B, this is showing a reaction. So this is the combustion of methane gas. So this is our reactant at the top, methane plus oxygen, which is giving us carbon dioxide and water. But when that methane burns in the presence of oxygen, you can see that if I compare the relative enthalpy of my reactants versus my products, that my reactants have a higher enthalpy than my products do. You can see that the delta H for this reaction is negative 890.4 kilojoules per mole. Since the sign is negative, that means that heat is given off by the system, the reaction. So heat is given off to the surroundings, and we call this an exothermic reaction. To summarize, the change in enthalpy, delta H, can be calculated using this formula. When my delta H is greater than 0, we call this an endothermic process. And when my delta H is less than 0, we call this an exothermic process. We've been talking about heat for a while, and the units that we use for heat, Q, are expressed in joules, J, so this is the SI unit for energy. We owe that to James Joule, who did a lot of experiments in calorimetry a long time ago. Although joules are the SI units for energy and they're most commonly used in chemistry class, there are other units that you can use for energy. So an alternate unit is what we call the calorie. And notice that we're using a lowercase c, so the calorie. And the calorie is defined as 4.184 joules. And notice that I said little c calories because when you go into a grocery store or in your cupboard at home and you look at any nutritional labels and it lists calories, the calories that you see on food labels, nutritional calories, those are big C. So notice this is an uppercase C. And an uppercase calorie, so the way that we define that is 1,000 little calories is equal to 1 big C calorie. 1 kilocalorie, and you think of kilo, if you think of kilograms, it means there's 1,000 grams. So 1 kilocalorie is equal to 1,000 little calories, which of course would be equal to 4.184 kilojoules, right? Because we're talking about kilo, 1,000. So again, the nutritional calories that you see on a food label, we use the uppercase C, and those would of course be equivalent to a kilocalorie. A thermochemical equation is a balanced equation that includes the enthalpy change, the delta H, for that process. All three of the processes we see on this slide are thermochemical equations. The first bullet point tells us that the stoichiometric coefficients always refer to the number of moles of a substance. So what we see here is that we're taking ice, so H2O solid, and it's being converted into H2O liquid. So we were basically melting ice. Now we see that the delta H for this reaction is positive 6.01 kilojoules per mole. And you'll remember that when delta H is a positive number, this is an endothermic reaction. Since it's an endothermic process, that means I had to put energy into the ice in order to melt it. So I could rewrite the equation as 6.01 kilojoules plus my ice being converted into water, like that. Now notice that I've left out the per mole, and the reason that I did that is because it's 6.01 kilojoules that I have to put in the reaction for how much? 1 mole. Well, it just so happens that the stoichiometric coefficient of my water is 1, of my ice is 1. Another rule is that if you reverse a reaction, the sign of the change in enthalpy changes. So for example, if I take that first process and I turn it around so that I'm taking my H2O liquid and I'm freezing it, so I'm converting it into ice. Now what I see is that this is an exothermic reaction because my delta H is a negative value. So the sign changed. The magnitude did not change because I just reversed the reaction, but the sign changed. So if the change in enthalpy is a negative number, this is an exothermic reaction, and I could rewrite the equation with my delta H value as a product. Notice again that I left out the per mole because it's minus 6.1 kilojoules that is being released per mole. But what are the stoichiometric coefficients of both of the H2Os? They're both 1, so I can just leave it as 6.01 kilojoules like that. And remember that my energy, my enthalpy, is going to be a product because it's an exothermic reaction. So if you think about it, as I take water and I'm cooling it down, as I freeze it, what's going to happen to that heat energy in those molecules as they're slowing down and they're crystallizing? It's going to exit, right? So an exothermic reaction. The last rule is that if you multiply both sides of the equation by a factor, n, then delta H has to change by the same factor of n. So if I take the first reaction on this slide and I multiply the whole thing by 2, so both of my stoichiometric coefficients become 2 instead of 1, I have to multiply my delta H by 2 as well. So when I reverse a reaction, the sign of delta H is going to change. And if I multiply both sides of the equation by a factor of n, I have to multiply my delta H by the same factor. Something else you have to be careful with when you're writing out thermochemical equations is that you have to include the physical states of all the reactants in the products. So if you take a look at these two processes here, if you were to just write H2O going to H2O, I mean, that would be meaningless. There's nothing happening there. So you have to specify. In the first reaction, I'm going from water in the solid phase. So I'm going from ice and I'm melting it. And I see that the change in enthalpy is positive 6.01 kilojoules per mole. So that's an endothermic reaction. That makes sense. I'm going to have to put energy into the ice in order to melt the crystal and convert it into the liquid phase. Now in the second process, I'm taking H2O in the liquid phase and I'm vaporizing it, which means that I'm converting it to a gas. And look at the magnitude of the delta H. It's still an endothermic reaction. I'm going to have to put energy in to get those molecules in the liquid phase, to get them moving faster and get them to escape the liquid phase. And we need more space in between the particles. In order to do that, I have to put in much more energy. So I'm going from 6.01 kilojoules per mole to melt ice to 44.0 kilojoules per mole to get water and convert it into the gaseous phase. And this makes sense because when I go from liquid to a gas, again, I'm going to need more energy because the particles have to be so much further apart from each other. This problem says, given the thermochemical equation, 2SO2 plus O2 gives you 2 moles of sulfur trioxide, gives us a delta H, which is minus 198.2 kilojoules per mole. So this is an exothermic reaction, and therefore it's asking us to calculate the heat evolved when 87.9 grams of sulfur dioxide is converted into sulfur trioxide. Well, the first thing I think we should do is figure out how many moles of sulfur dioxide we have, because obviously we don't have 1 mole. So let's start with that and we'll figure that out. So we have the mass of our sulfur dioxide, 87.9 grams of SO2. And we know that in 1 mole of SO2, there's 64.07 grams of SO2. So our units of grams of SO2 are going to cancel out and we end up with 1.37 moles of SO2. Now, we figured out the number of moles, but our delta H is given to us as minus 198.2 kilojoules per mole. Well, per what mole? Well, the answer is it means per 1 mole of oxygen, per 2 moles of sulfur dioxide, and per 2 moles of sulfur trioxide. So it's important that you know how to interpret that change in enthalpy with respect to your balanced equation. So if the change in enthalpy with respect to sulfur dioxide is minus 198.2 kilojoules per 2 moles of sulfur dioxide, I can use that as my conversion factor. So if I have 1.37 moles of sulfur dioxide, I'll use my conversion factor, which is 198.2 kilojoules per 2 moles of sulfur dioxide. My moles of sulfur dioxide cancel out, and I end up with minus 136 kilojoules as being equal to my delta H. Now let's do a comparison of delta H and delta E, so our change in enthalpy versus our change in energy. Let's examine this reaction here. So we take sodium and we react it with water, and we end up getting sodium hydroxide and hydrogen, and this is a very exothermic reaction. It's shown down here in the bottom left in this picture. Now if we want to calculate delta E is going to be equal to delta H minus P delta V. We've already been given the delta H value, which is right here. And where is the pressure volume work coming from? Well, if you look at the sodium, it's in the solid state, the water is a liquid, and the sodium hydroxide is an aqueous solution. We're only forming gas here, and it's 1 mole of hydrogen gas that's being formed. So at 25 degrees Celsius and 1 atmosphere, 1 mole of hydrogen has a volume of 24.5 liters, and I solved for that using the ideal gas equation. So if I plug this volume into my P delta V, I get that my pressure, which is I'm running the reaction at 1 atmosphere, I multiply by the volume, and then I convert the units of ATM liters into kilojoules, and I get that it's 2.48 kilojoules. So when I plug this into my formula, my delta E is equal to delta H minus P delta V. I get that delta E is equal to minus 367.5, and then I'm just going to subtract this little 2.48, and I end up with minus 370.0 kilojoules per mole. So if you look at the difference between my delta H, which is highlighted in yellow, and my delta E, you can see there's actually very little difference between the delta H and the delta E of this reaction. The conclusion that we can draw from this is that knowing the enthalpy change of a system tells us a lot about its energy change as well. In fact, because many reactions involve little, if any, pressure volume work, most, or sometimes all, of the energy change is due to the transfer of heat. Now, our book discusses 3 specific cases, so let's take a look at them. The first one is reactions that don't involve any gases. Now, gases do not appear in precipitation reactions, most acid-base reactions, and a lot of redox reactions. For example, if we take a look at this neutralization reaction between potassium hydroxide and sulfuric acid, you can see that everything is either an aqueous solution or a pure liquid. So there are no gases involved in this reaction. Now, because liquids and solids undergo very, very small volume changes, like when you mix solutions, you can get volume changes, but they're very, very, very tiny. So essentially, our delta V is going to be almost 0. So I'm going to put almost 0, very close, approaching 0. And if that delta V, if it's so small that it's approaching 0, then the product of pressure and volume is going to be almost 0 as well, getting very close. So let's see what happens when we take our equation. Delta H is equal to delta E plus P delta V. Well, again, if the P delta V is almost 0, this is going to essentially cancel out. And what I end up with is that my change in enthalpy is going to be almost identical to my change in energy. Another case is reactions in which the amount or the number of moles of gas doesn't change. When the total amount of gaseous reactants equals the total amount of gaseous products, the volume is going to be constant. So again, my delta V for this reaction is going to be equal to 0. I have 2 moles of gaseous reactants, and I form 2 moles of my product, which is also a gas. And we know that the volume of an ideal gas is not dependent on its identity, it's only dependent on the number of moles. So since the number of moles isn't changing, my delta V is going to be 0. If my delta V is 0, well then, again, my P delta V is going to be 0, and my delta H, which is equal to delta E plus P delta V, is going to reduce to delta H being equal to delta E. The last case are reactions in which the amount or the number of moles of gas does change. In these cases, the pressure times delta V doesn't equal 0. However, the heat produced at constant pressure, the QP, is usually much larger than P delta V. So delta H is still going to be really close to delta E. So for instance, let's take a look at this reaction. It's the combustion of hydrogen. We have 3 moles of gas over here, 3 total moles of gas, right? 2 and 1. And then we're producing 2 moles of gas. For this specific reaction, the delta H, I'll write it down here, is equal to minus 483.6 kilojoules. And the P delta V, I've already gone ahead and calculated that, is equal to minus 2.5 kilojoules. So if I use my formula, delta H is equal to delta E minus P delta V, I can rearrange and solve for delta E. So my delta E is going to be equal to delta H plus P delta V. And when I plug those numbers into my equation, I get minus 483.6 kilojoules. Subtract negative 2.5 kilojoules. And I get that my delta E is equal to minus 481.1 kilojoules. Thus, since most of this delta E value comes from the delta H, which is the energy transferred as heat, we can say that our change in enthalpy is very close or essentially equal to our change in energy. Thus, for most reactions, delta H equals or is very close to delta E.